Good morning. In the first part of today's lecture, I want to talk about a couple of extra stuff related to the model validation for biological feasibility. Or in other words, what are the conditions that we need to verify so that the model is biologically feasible? I'm going to go a little bit in depth in what we mean by these terms. I just want to point out that this will not be a major focus on our course. The vast majority of models that we can build, one can prove with similar techniques that they are biologically feasible, to the extent that some of those proofs are not even done anymore in research papers if the model is a typical model, because the technique of proving feasibility is pretty much the same for a large class of models. Often, though, you could have surprises in which the math is not that obvious and you need to actually take the time to prove it with some more advanced techniques that I don't want to get into. I think it's important, though, even in an introductory course like ours, to at least be aware of this concept of what we mean by a model to be biologically feasible. Because it's important to understand the limitations and the possible problems that models can have if one is not careful. This isn't about the math correctness of the model, but whether the model is built in such a way that makes sense from a biological perspective. So I'm going to basically illustrate briefly with a couple of examples. So let's do one for which I'm not going to actually get into how to check it. It's a little bit more complex, especially if you cannot actually solve the system explicitly, which is the case most of the time. So for example, the model, the solution, should be defined for all time t greater than 0. Most of the time you want to run the model in forward time. It doesn't have to. I mean, you can construct a model and analyze it backwards. But let's keep it as a standard that, the goal is to basically start with an initial condition and want to know what happens in the future. You want the solution to be defined for all time t. For example, you don't want, let's say, something like this. Let's say a population that has a vertical asymptote. So let's say P of t, the solution of the model, let's say is something like 1 over 1 minus t. Now, if you were to sketch the graph of this function, there's a vertical asymptote at 1. So let's see, if you approach 1 from the left side, that's going to be basically positive infinity, right? So this it starts from 1 t equals 0, goes like that, vertical asymptote, and then minus infinity, and as t goes to infinity, it approaches 0, right? So that's the graph of 1 over 1 minus t. What is the problem with something like this? Again, nothing wrong from a math perspective. So the theory of differential equations states that if you start with an initial point, let's say the initial point P of 0 equals 1, then the solution looks like this. But notice it's not defined for all time t. It breaks down at 1 in the form of a vertical asymptote. So the problem with this, not only is that something is wrong built in the model that it doesn't allow you to predict what happens, beyond times t equals 1, but it also predicts that P of t goes to infinity in finite time. In the language of modeling, this sometimes is called blowing up in finite time, which is not biologically correct. So notice I'm not talking about realism, right? Because if you have an exponential ODE, in the case of an exponential ODE, you have P of t going to infinity as t goes to infinity. So if you run the movie indefinitely, right, if t goes to infinity, you could have the population going to infinity, which is not realistic, but it's still feasible from a biological perspective. In other words, under ideal situations and ignoring all limitations of space and resources, If you have positive growth rate, obviously the population may go to infinity in the context of that model if t goes to infinity. But going to infinity in finite time, meaning that as I approach time t equals 1, at that point in time you have an infinite population, that doesn't make sense from a biological perspective. So, I mean, in other words, nothing special should happen as you pass time t equals 1, in the sense that the population at that moment of time should have a number. Might be unrealistically high number, right, if the model is not realistic enough, but it's got to be a real number if I specify a point in time. So if it was, for example, a billion population, you know, at time 0.9, there's got to be a number, whether it's 3 billion, trillion, whatever, but it's got to be a number as I plug in the point t equals 1. So that's one of the problems which, for now on, in our course, we're going to assume that we won't meet. In other words, our models that we're going to deal with are defined for all time t. Sometimes these type of problems appear in models, and they are subtle enough that you actually don't notice them unless you actually sketch and plot the solution. And then the question is to maybe change the model assumption so that you avoid this problem. Another obvious problem with biological feasibility is the so-called positive invariance. It's not a fancy name. The model should be positive invariant, meaning that if we start with positive initial conditions, then the solution should remain positive. Or 0. In other words, it shouldn't cross on the negative side. The reason why that's the case, it's obvious, right? I mean, if you have a population, let's say the P of t, the population that is the solution of your model, if you start with a negative quantity, it does something like this. If you start, let's say, with a negative quantity, maybe it does like this. I don't really care what happens, basically, if you start with an initial condition negative. So when P of 0 is less than 0, we really, sorry, this is out of range again. So if P of 0 is less than 0, we really don't really care about P of t. Because if P of t represents a population size, the only possible initial condition is a positive initial condition, 0 or positive, right? You can only start with no people in a certain category, no individuals, or a positive number of individuals. So whatever the math, that's why actually when we run the models in the p-plane or d-field or these plotters, we really look at the basically at the range in which p is positive. We don't really start the model with a negative quantity. On the other hand, if you say, let's say you have a population model and you start with a positive quantity, let's say you start with P of 0 equals 10 or something like that, and let's say the population goes like this, so that means at a certain point in time in the future, P of t becomes negative. Again, doesn't have to be negative all the way through, but it's got to be, if it's negative for a portion of time, then we have an invalid model. Okay, because something is incorrect in the build of the model. Either there is a, well, I mean, assuming, of course, this is truly the property of the model. I mean, assuming there is no math error. But if your model predicts this, then it's an invalid model, at least if you want to use the model for the whole time range, because we should make this qualifier. If your excuse, the modeler excuse, is that the model is used just for a short period of time, and in that period of time, let's say we don't have this drop in the negative category, you can get away with that excuse and say, well, yeah, I mean, the model is valid for the time range that I want to. Personally, I mean, this is a personal opinion, because there are plenty of models which are invalid for the whole time t, yet they and I'll show you an example maybe later. And they are used nevertheless under this excuse that it's used just for a short period of time. Personally, I don't actually like that type of excuse because it can hide incorrect assumptions in the model. Maybe the reason it drops on the negative territory is because there is something intrinsically wrong in the biological assumptions that you make when you build those terms in the model. So in this class, I went over how you actually show positive invariance, and I'll show you basically two basic techniques that are used very often, and they are so standardized that they are not even mentioned basically in the models. Sometimes papers mention something on the line like, you know, the solution is positive or the model is biologically feasible, which can be proved by standard means, and that's it. They don't actually show the means by which they prove that. And you know, if that's the case, then, you know, in research papers one doesn't have to do that. So let's go over actually these. Maybe let's make it actually a second part in which I'll show you the two standard techniques in how to check that the solutions remain positive if they start with positive initial conditions. So stay tuned for the second part.